Welcome to Lesson 4 of the unit on exponential functions. This is the unit on how to change bases. I want you to think back to another unit that we had on radicals and the different type of stretch that happened in the graph when we went from a, let's see, it was like, trying to think what it was. It's like x squared, and we had a 3 here. What kind of stretch was that when we were graphing? I know this is a U-shaped graph, but this a value caused a vertical stretch. Remember, it came off of the x-axis, and instead of going at 0, 0, and over 1, up 1, you would go over 1, up 3, because it was a factor of 3 that you were stretching by, so it made that U real narrow. Now when we put it as the inverse and we flipped it over the xy line and we came out with a radical 1/3 x, we said that that was a horizontal stretch because it pulled it this way, and so our horizontal, though it looked like a shrink if it were in the vertical position, it actually became a horizontal stretch because it was inside of this radical in here. Okay, so I just want to mention that before we get into this one. Now here we're looking at the number up here in the exponent. Okay, different type of function, but you'll see a similarity here. If we have 2 to the 3x, then we take 2 to the 3 times -1, so that would be 2 to the -3rd, which we would write it on the bottom to make it positive, so it's 2 to the 3rd, which equals 1/8. Now we come over and we graph that. At -1, we are at 1/8, so it's way down here. 2 to the 3 times 0, well, 3 times 0 is 0. So 2 to the 0th would be 1. 2 to the 3 times 1, that's going to be just 2 to the 3rd, which is 8. 2 to the 3 times 2 is 2 to the 6th. Multiply that out, it'll be 64. And 2 to the 3 times 3 will be 2 to the 9th, which will be like 512. Okay, so now we go to the graph, 0, 1. As we've seen, if there's not a stretch, a vertical stretch occurring, then it's going to go right through there. So we know this 3x doesn't create a vertical stretch. Okay, the only other thing that would cause it to not go through the 1 is actually a vertical stretch won't, let me think this through. Vertical stretch, yes, can create that. The only other thing that could cause it to not go through the 1 would be if we had a shift in our k, but there is no k value here. So we know that it's not a vertical stretch. So now we want to look at what's happening to the graph. We go through 1, 8, 1, 8. So we see the graph go right along here and then way up here. So now I want you to look at the horizontal. What would you call this? And think back to in previous things on the horizontal. This was a horizontal stretch when it was a fraction. So this being a whole number in the horizontal position, and looking at the graph, what's the distance from the y-axis over to the new one and to the parent function? So we would call that a horizontal shrink. Okay? Next one, if we have a -3, what do you think would occur? I want you to plug in these values. 2 to the -3 times -3, we plug in right there. That'll become 2 to the ninth, which is 512. 2 to the negative 3 times negative 2, that'll be 2 to the sixth, just like here. So that'll be 64. 2 to the negative 3 times negative 1 would be 2 to the positive 3. So that will be just like up here at the 8. 2 to the negative 3 times 0, that would be 1. And then 2 to the negative third will be the 1/8. So if we plug these in, negative 3, 512, we can't even come close to graphing. Negative 2, 64, we can't get even close. Negative 1, negative 1/8, 0, 1, and then 1, 1/8. So it is flipping it over the y-axis, doing a reflection of the y-axis when we have a negative in that position. Okay? Now we go to this one. Well, if we look up above, the 3 caused a shrink to the y-axis. What do you think the 1/2 will do? Go ahead and graph these points. 2, 1/2 times negative 4 would be negative 2. Half of negative 4 is negative 2. So that's 1 over 2 squared, or 1 over 4. Negative 2, half of negative 2 is negative 1. So 2 to the negative first would be 1 over 2. 0 times a half is 0, so 2 to the 0th would be 1. 2 times a half is 1, so that would be 2 to the first. A half of 4 is 2, so it's 2 squared. Now, we go ahead and we put that on the graph. We would have negative 4 at a quarter, negative 2 at a half, 0 at 1, 2 at 2, and 4 at 4. So now look at what's happened to the distance between the y-axis and the parent graph compared to the y-axis and this transformed graph. So with a fraction in there, it's creating a horizontal stretch. The whole number created a horizontal shrink. And the negative in there flips it across the y-axis. So now here, they're going to put a negative in there. Hopefully you can already picture that it's going to be this reversed going this way. Okay? It'll still be a horizontal stretch. It'll be a negative, so it's flipped over the y-axis. Okay, next page. Again, tomorrow we'll be going over this in class, so if you have questions or need clarification, please ask in the warm-ups. Look at your graphs to make a conjecture. This is exactly what I've just talked about. So look at your graphs to make a conjecture when c is greater than 0. How is the graph related to the graph of the parent graph? So when c is greater than 0, here's an example on A. Okay? Here's another example on C. So they're just wanting to know about that reflection on the y-axis. Then it says, when c is less than 0, how is the graph related to the parent graph? Okay? So they're really getting at that reflection. You need to explain it in your own words, though. Okay, down to the next thing, comparing the graphs. It says, for each row of the first table, enter one function. We're using a graphing calculator. What do you notice about the graphs for each pair? So we'll go into, if you get that, it goes quit, second quit, clear. Okay, go into our y equals. We're going to enter 2 raised to the 3 alpha x, move it up here where you can see what I'm doing, alpha x, closed. That is our first graph that they want us to look at. Now we go to the second graph. They want us to look at 8 raised, whoops, okay, 8 raised to the alpha x. And now we just need to go to the graph and see how these appear. First, let me check the window. Okay, window should be good. Let's look at the graph. Here's the first one, 2x to the third. And there's the second one. They graphed over the exact same line, so those are equal. Let's go to the next one. 3 raised to the 2x compared with 9. Let's go to the graph. There's 3 raised to the 2x, and again, the 9 to the x is right over top of it. Last one. 1 divided by 2 raised to the 2x, and 1 divided by 4. 1 divided by 4 raised to the x. We'll graph it. There is 1/2 raised to the 2x, and then there came the 1/4 raised to the x. So each of these are the same. What do you notice about the graphs for each pair? They are the exact same graph. Okay. Now, what's interesting, it says, how can you use properties of exponents to explain this observation? Well, here's our properties of exponents. 2 to the 3x is equal to, how can we simplify that? We could say it's 2 to the third raised to the x. Now, what is 2 to the third? That would be 8 raised to the x. And now you've proven why these are the same graph. Okay? So that's again, now you need to go ahead and do this for the next two. 3 to the 2x, you need to prove how it's equal to 9 to the x, and 1/2 to the 2x, you need to prove how it's equal to 1/4 x. Okay? If you can't do that, that's a great question to ask in class, but follow this pattern. Okay? Next one. Repeat the process for the functions in the second table. What do you notice about the graphs of each pair here? Okay? Well, this should be interesting. Now we're going to look at y equals, we're going to put in 3x. Delete that, delete that, delete, delete. 3. We can do delete, delete, over, delete. Okay, 3 to the x compared to 1/3 to the x. Let's see how that graphs out. There's the 3 to the x, and there's the 1/3 to the x. How are those two related? How would you describe the relationship from this one over here to this one over here? Let's go ahead and look at the next one. 5 to the x compared to 1/5 to the x. There's 5 to the x, and there's 1/5 to the x. Okay, next one. We want to go 3 3 halves to the x. 3 divided by 2 halves to the x. And on the next one, we want to go 2 divided by 3. There is 3 over 2 to the x, and there is 2 over 3 to the x. What are you noticing about these graphs? Hopefully you said that they're a reflection over the y-axis. Reflection over the y-axis. Okay? How can you use properties of exponents to explain your observation in step B? Well, we know that 1 over b equals b to the negative 1. Okay? And we also know from our front investigations that b to the negative 1 is a reflection over the y-axis of b to the 1. Okay? Now we can take this 3 to the x we want to keep it equal, so if we move that 3 to the bottom, it has to become a negative 1 in order to keep it equal to that 3. Because we've moved it to the bottom, it would become a negative 1. Now that, compared to this, because of the negative here and the positive here, this is a reflection of this one. Okay, now you need to show it on all of these, how they're all reflections of the other one. For what value of b are the graphs f of x equals bx and g of x equals 3, negative 2 to the x the same? And explain. Okay, so if we think about that, we need to just simplify this part for the b. Okay, so we know that f of x will equal g of x when b of x, which is the f of x, equals 3 to the negative 2x. Okay? The x's are the same, so we just need to simplify this 3 to the negative 2. We can simplify it by putting it on the bottom. 1 over 3 squared equals 3 to the negative 2x. 1 over 9, oops, we should have kept the x in there for the b. 1 over 9 to the x equals 3 to the negative 2 to the x. Okay, and that's kind of how we start changing the base. A lot of how we're changing the bases. Okay, here we go. We're going to get into a little bit of fun here. So, write two equations for the exponential function whose graph is shown by choosing two different bases. Okay? First off, the horizontal asymptote is the x-axis, so there is no vertical translation. There's no k value because the asymptote's right here. The function rule may be written in the form ab to the x. So we know all that we're looking for is the a value, the b value, and the x value. The graph passes through 0, 1, so we know there is no stretch. That means a is equal to 1. The graph also passes through 1, 4. So now this helps us to find our growth rate. That means that 1 times what equals 4 because we're moving up by that amount. So we have a b value. That would be 4. Now let me make sure that you understand, another way that you could look at that is ab to the x equals 4. We know that a is 1. We don't know b, but we know that this is the first power. The x value is 1. And the y value is 4. So we can solve for b, and we come out with 4. So an equation for the function is f of x equals 4 to the x. We don't need to even put the 1. Change the base. So we take f of x is 4 to the x. Write the base of the function as a power. So how can we switch 4 into being a power? If you said 2 squared, you're correct. Now we just bring it back into the exponent, 2 to the x. Okay? So another equation for the function is 2 to x. Show how to write the exponential function with a base of 1/4. Well, all we need to do is bring 1/4 back to equaling 4. That would be 4 to the negative 1. And now we just need to bring the x in. No, that wouldn't be right. That wouldn't be the same as that one. We need to go the other way. 4 for the x could equal, in order to keep this equal, would go down to 1/4. Pencil lead's running out. 1/4 equal to 4 would be negative 1 x. So that's the correct answer, not this one. I went backwards on that one. Let me just grab a new pencil. Or a pin. I can do it with a pin here for a minute. Okay, now we're going to look at money. And we've talked about exponential growth with money in the past. So I just want you to read through this. The P is your principal. R is a fixed percent. It's a rate. A of T is the account after T years. You're trying to find out what the balance is after T years. So T is the years. N is the number of times per year that it's compounded. That means the interest. And you might hear the term nominal rate. That's represented by your rate divided by the number of times that it's compounded. Later on here, the effective rate, you remember me showing you that in order to get the rate of increase, the rate of growth, you needed to take the 100% or 1 as the whole number and add it to your rate. Now we need to make sure and divide it by the number of times it's compounded and raise it to the number of times it's compounded. But then we need to subtract the 100% back off of it so that we only see the rate that it's growing. So that's the effective rate. And I think that'll get you through. Please stop and read that, see if you have any other questions. This is the most common equation to be seen. Okay? This R just represents all that stuff in there. Okay? Let's go to the next page. Arturo plans to deposit $850 in one of the accounts shown in the table. Okay? He chooses the account with the greater effective rate. How much money will he have in his account? Well, first, we need to decide which one has the greater effective rate. So in account X, we see that it's compounded quarterly. That would be 4 right there. The nominal interest rate is 2.5%, so that would be 0.025. Okay, now we have our formula to plug in. So we put our rate on top, 0.025. Number of times it's compounded, the 4, and raise it to the 4. Now, when you plug that into a calculator, so I can quit there. If we do this, whoops, let me back up. Parenthesis, 1 plus 0.025 divided by 4, parenthesis closed, raised to the 4th, minus, oops, we don't want that. We don't want it up above. Minus 1 equals 0.025235. It says to round it to 5 decimal places. So 0.02523 is 5 places. There's a 5 next, so you'd round that to 4. Okay? Go ahead and fill that in right here on the blank. Now we go to the other one. So for account Y, the interest rate compounded monthly, so N is 12, because there's 12 months in a year. Nominal interest rate, move it over 2 places, 0.0248. Now we go ahead and we fill it in. So it's 12.0248. Now you're going to take, just like you did before, 1 plus 0.0248, whoops, 48, divided by 12, parentheses closed, raised to the 12, minus 1 equals. Okay, the effective rate for that is 0.2508. So now you'll compare 0.2508 with 0.2524. 524 is bigger than 508, so the account that has greater effective rate is X. So we're going to be using this formula. Now we come down here and we actually plug in the amount of money. It's going to deposit $850. There's our principal. That's our P. 1 plus, the formula we went with, is the effective rate of 0.025 raised to the 4th, quarterly compounded. And now we need to think, how many years was he going to invest it for? Up here it said 5 years. So we need to make sure and multiply it by our time to see how much money he'll have. This is actually how you can figure out the amount of money in an account and see if it's worth it to you. Okay, so we have 850 parenthesis 1 plus 0.025 divided by 4, parenthesis closed, raised to the 4 times 5. Okay, $962, and this is cents, 80, there's a 1 there, so it would be 80 cents. Okay, so that's what you'd fill in here. That's also what you'd tell here with the dollar symbol here. How can you use the effective rate to find the amount in Arturo's account? Well, the effective rate, once we had it, we just plugged in his principal, the amount of time he was going to put it in there, and then we had the answer. So put that in your own words. This is the practice. We'll do it tomorrow in class. Thank you.